You guys have been competing for a few years, and we're with the lacrosse team right now. How long has the AICC challenge been going on for you guys?
So it's been about 2 years. The announcement was made earlier, and we submitted a white paper. We were one of the 7 teams that were funded by the government to participate in the original semifinal competition, which was started 2 years ago. And then at DEF CON last year, it was announced that our team had made it into the finals. So then we had one more year a little less than a year to work on the system further. The challenges evolved as well, so the whole thing didn't stay the same. And we had to basically build the system again to compete in the finals.
So I guess before we dive into the details, because I really want to hear the details, can you give me like a 30-second high level, what is the AI cyber challenge?
So the main point of the challenge was to find and fix software flaws that were either artificially introduced into large open source projects or were replaying old bugs that had been in those open source projects that had been fixed. And then our system was designed to fully autonomously find those bugs and then fix them by itself. And it ran for 6 days or so, continuously doing that with no hands-on.
So what's so cool about this is, I'm probably gonna. You guys call it AI, large language model, or is it a little combination of everything?
So our team used a combination of traditional software analysis tools like fuzz testing and symbolic analysis kinds of things, and large language models, which was really the new thing for us. We've been doing large-scale fuzzing projects for many years. We have an existing large-scale architecture for tasking hundreds of compute nodes to do fuzzing or other kinds of software analysis. And the new thing here in the Cyber Challenge in the last 2 years was adding large language models into the tool suite that our system can use. And it uses them for several things. Finding flaws, they can do that all by themselves, and creating potential inputs that might trigger those flaws. They're not very good at that, I will say. And then patching the software itself. So once you find a flaw and you can trigger a crash in a program, for example, you can ask the debugger, hey, where did it crash? And then you could perhaps collect up some of the information around there and feed it to the large language model and say, can you fix it?
So high level, you were given a code base, Apache, something like that, may have had artificial ones, may have been an old exploit. You had then to create a pipeline, which will first identify a bug, locate a way to trigger that bug, write it up and report on it, create a PR for it, and create a test case to be able to verify whether or not the bug has been closed. And that had to be completely autonomous from start to finish. That is a heck of a lot of work. So when you first heard about this, what was your approach?
Well, as I mentioned, we've been doing this for a while, and 10 years ago or so, DARPA funded a Cyber Grand Challenge, so the previous competition, and our team participated in that challenge as well. So this architecture that we have for doing fuzzing and building patches in the Cyber Grand Challenge 12 years ago, that only worked on binaries, no source code, and they weren't very large-scale programs. But we already had all that tooling to task hundreds of nodes, how to fuzz test and use other analysis tools. So we basically started with all that in our back pockets, and then we started integrating large language models.
So how big is your team?
So our team is all at the company called SIFT, Smart Information Flow Technologies. Our company is about 35 people, and over the course of the 2 years, about 15 of those people worked on the project on and off.
What was your specialty on it? Because was inside a team, is everyone kind of have a specialty, or does everyone kind of generally touch every piece of it?
Well, we had some people who touched just about everything, like Lewis here.
Touched a little bit of everything, yeah.
Yeah, and then we had some people who were really specialized on, for example, large language model wrangling, or wrangling the fuzzers and things like that.
So walk me through your setup. You would have code. How would you? What would be the initial trigger? Code comes in. Where does it go? Is everyone had a different approach? So code comes in. What was the first thing that you did with it?
Yeah. So we get a code repository from the challengers. It'd come in through a Python API, and we feed it to one. We have our Optimus primary agent that dishes it out to a bunch of other agents that then start fuzzing it and working on it.
Would you use open source? Are we using open source tools, a commercial tool to do the fuzzing?
Mostly open source stuff now. It's all going to be open source on August 24th. So, yeah, we pretty much fuzz it, and then we start feeding it off into LLM pipelines to see, like, hey, we found this vulnerability thanks to fuzzing, and then we would give it the vulnerability we found, and the LLM would either say, yep, this classifies as this. We'd get the description. We would run some tests on the description and see, is it right, is it wrong? And then we'd requery the LLM with that new information that we get.
So obviously AI is all the rage right now, AICC. Just how bad were the models at doing this when you started versus where you got to? Because I think that's the really, not the most interesting piece, but I think that's the thing that everyone knows now. It hallucinates to hell. It gets things wrong. It can't do math. It can't do that. Did you find, did it get easier over time? Did it get things more right over time? Or did it devolve? Did you stick with one particular model? Did you have to migrate to different models? Like, how bad was it at the beginning? And did you actually manage to wrangle it?
Mm-hmm. So in the semifinals, we were given like a pretty constrained amount of LLM budget. I think only free tiers were available for us with OpenAI and Anthropic. And I think Google was in there as well. And then it was really cool to see in the finals, they kind of unlimited those constraints. And we were able to use any models that we could possibly choose from all those providers. And they kept kind of supporting other providers as well. I think XAI eventually was involved in that too. And yeah, throughout the entire course of the finals, we were shuffling around our model lists all the time. What model do we want to use as our primary model? Like, we want to focus on O3 the most, or do we want to focus on Sonnet 3.7? Like, which one we want to choose? And it was a lot of debugging and testing to figure out which model is proving the most accurate for us and what we're using it for.
Yeah, but we didn't use just one. We had a lot of stuff that did sort of portfolio queries out to the LLMs and said, all right, let's get 6 or 7 or 8 variants of the answer and see which one looks most representative. So there are a number of places in our code where it would send the same query or minor variations in the query out to different LLMs, get back the results, and try and look for commonalities to try and weed out the hallucinations. But a lot of it was also tested. So after a patch was generated, we would have to make sure that the code built and passed any tests that we had and wasn't no longer subject to the vulnerability that we discovered.
So you did fuzz testing. Did you use any other like standard static code analysis tools, package analysis, or anything like that?
So if you come to our talk tomorrow, we'll put up a diagram of kind of all the things we plan to do, and then there are a bunch of red X's through a bunch of boxes that either didn't work or never got integrated. And static analysis was one thing that we really worked hard on in the semifinal competition. We never really found a tool we thought was working well enough to be included, so it's got an X through it. Static analysis.
Was it mostly open source static analysis tools, or did you throw as whatever, like Coverity I think is paid and things like that?
We didn't have any licensed software.
Gotcha.
So your entire model is going to be open source as part of the requirement for the contest.
Right.
Your entire model is going to be open source.
Well, when we use the term model, we're usually talking about large language models, and we did not fine tune our own models, so we were just using the ones that you can pay for now that Lewis listed them, some of them. But our entire software system, which we're calling Lacrosse, is going to be open sourced in a couple of weeks.
So what did you program? You have this model, so it's going to pull things in, and you almost have like an orchestrator, which is moving it across the different stations. I'm guessing that orchestrator you created was a custom orchestrator.
No, the orchestrator is actually an adaptation of the one that we used in Cyber Grand Challenge, which is actually an adaptation that goes way back. Doing multiple autonomous systems originally was what it was designed for. Tasking unmanned air vehicles was the original start of that stuff. And a lot of that code is still in there. Everybody's going to get it open source, so you can all look, and it's all Lisp.
So
That's our secret sauce.
Yeah.
So I'm curious. Was this your introduction to DEF CON, this challenge? Or had you guys been coming to DEF CON for years and then saw this challenge and you're like, oh, this is something we have to get involved in?
This is only my second time at DEF CON, so I'm not a regular.
This is my first DEF CON, but I've always wanted to come. I used to see all the talks online back when I was in grad school, so pretty excited to be here.
So as you guys were building the model, there's probably two things that you came across. One, something which was completely unexpected. You started going and like, man, that was not something I expected in the challenge, and that was really interesting. Or you hit this problem and you're like, I have no idea how we're going to solve that. And I want to start with the problem. So somewhere along the line, what was the biggest problem you had throughout the challenge?
Probably scaling and adapting to cloud. We had to make sure our system run autonomously through Azure, and that was something that had changed between the semifinals into the finals. And that proved. I mean, I think that was one of the things that I worked on the most. So to me, that was very challenging to take kind of what we had developed previously that was running in Kubernetes and Docker, and just kind of throw it on to this multiple virtual machine system in the cloud.
Yeah, I think there was that. And then I wanted to get, before I forget, I want to answer the question about the surprise, because I think I have a pretty good surprise, which was we did a lot of testing of the LLMs with preliminary manual analysis before we started building the APIs and automating all of that. And one of the things that we found, which really surprised me, was sometimes the LLMs would not fix the problem correctly. You could tell them, hey, would you please go back and try again? Here's what the compiler said was still wrong. And what shocked me was that once I saw it manually, I gave it the manual feedback like that, and it said, okay, I've fixed that. And by the way, I'm going to fix a whole bunch of other things in the code that I think are stylistically wrong, and you shouldn't do it like this, and I'm going to fix it. And it fixed like 6 different things that I didn't want it to do. And that was a surprise, and it was also a bad surprise because we really didn't want it messing with any code that we didn't think was the actual source of the flaw, because we were afraid it would disrupt the performance of the open source system.
So one other question, I'll add it off. You're right, actually. I'll hand it off.
Yeah. I was like, it's really funny because that's basically what junior developers do. They're like, oh, I fixed that thing you asked, and I also fixed 12 other things, and it's all in one patch, and you're not going to be able to review it. So it's basically an intern, which I've been saying for a really long time. A lot of these models are operating at the level of an intern.
It kind of is, and it would have gotten fired because, I'm always telling guys, don't change anything that doesn't actually have to be changed. And that's what we had to tell the large language models.
So one of the things, there's all these like little weird nuanced tricks with large language models. Like one of them, like which just came out, which was take a breath and then give me the answer. And it's really unknown why that helps give it a way better answer. Was there kind of unique tweaks that you put in the large language model where it's like, oh, take a breath and then answer or something like that?
So this is one of the things that I think, to answer your earlier question about what changed during the 2 years, is that it used to be you'd say, I like cats, and could you fix this software problem for me? And it would get better. I don't think that's true anymore. The large language models got dramatically better at understanding and fixing software, which is exactly what we needed them to do. And you can still tell that you're a computer science expert. We do, but it doesn't make much difference anymore.
Interesting. It's funny because like as time has gone on, we've figured out how to use the models better, and they change, and then they abstract and things like that. How often were you finding when it came back with the software patch? How were you developing ways to pull in that code, normalize it, and then create the unit test? Was that difficult to do?
You want to talk about that?
Yeah, I mean, it was quite a challenge, but we used like a DSPy pipeline, and we would alter the prompts whenever we got code that we weren't satisfied with, or got like a return on a patch that we weren't satisfied with. And I mean,
that's another thing that changed during the 2 years, not just the budgets that we were given, but the scale of what you can feed into the LLM and what it can give back out went dramatically higher. So when we started, the token limits on the input were tens of thousands of tokens. And so you had to be very, very careful about what code you were giving it. You couldn't generally give it a whole code file from, let's say, Nginx. Any of the individual code files is too big. That's no longer true. If you pay enough, you can send in 300,000 tokens now, and a large number of source code files will fit into that. So that the things can now take in the whole source code file and spit it back out, modified.
So hindsight's 2020. having gone through the whole contest now, like everything's about to get open, you're doing your presentation later. What would you have done differently, having all the knowledge you have now in your process and your build out?
Well, the infrastructure turned out to be a tremendous challenge for our team. And one of the things we talked about is, we're bringing forward this ancient Lisp architecture that has been adapted to work in Docker containers, no problem, but it's still talking old school stuff. And we talked about going clean slate and starting from scratch. And I think if we had had enough staff, we would have done a parallel approach, and we would have said, you sub-team go start from scratch, make it all Pythonic, and don't try and bring forward all that old stuff. We didn't do that because we just didn't have enough time, person time, to staff both things.
Cool. Well, hey, thank you, Lacrosse. Thank you for taking the time to talk to us. Really, congratulations, man. There was like what, 40, 50 teams that competed. You guys were in the final set. Congratulations. That is a huge accomplishment. So thank you for taking time to talk with us. Thank you for watching. And
Thanks, guys.
hack on.